Welcome. Today's lesson is about statistical inference, or introducing the idea of confidence intervals. So a confidence interval is based off of our significance level. So like we've talked about in chapter 2, significance level is normally going to be 5%. So that means our confidence interval is like the opposite, so 95%. Now this can change just like our significance level. But what confidence interval is describing is based on the sample statistic that we find, whether that be p-hat or sample mean. We're describing what probability that our actual long run proportion or our population mean will fall within 2 standard deviations of the p-hat or sample mean that we found. And so there will be 2 different numbers based on that. Okay, so for example 1, we're talking about whether a dog can sniff out cancer. Dogs have a great sense of smell, so researchers wanted to see if a dog could kind of locate or figure out if a patient had cancer of some kind. And so they had this dog, Marin, that is an 8-year-old lab. She was trained to sniff out certain bags, was rewarded with tennis ball. So the test, once she knew what she was supposed to be doing, they had 5 bags that patients had breathed into, one of which was a cancer patient. The other 4, we're not told what they have. So her job was to sniff out which one she believed had cancer or was from a cancer patient, and then she would sit next to it, and then the researchers recorded it. Okay, she did this 33 times, and so we're going to kind of go through our process like we normally do, but adding in confidence interval when it's appropriate. So the researchers asked, can dogs smell if a patient has cancer? Pretty straightforward. So then they set up the study with the bags. So there's 5 bags, one of which is breathed in by a cancer patient. So the probability, if it's just random, would be 1/5 or 0.2. So for our null hypothesis, we'll say our parameter is 0.2. So notice it's a proportion, not a sample mean, because it's a probability here. And so then our alternative will be not 0.2. Okay? So once they did their study, in her 33 attempts, she found the cancer patient's bag 30 times. So her statistic was 0.9091 for that. And so looking at our data and putting in the proper things, so for our null and our alternative not equal to, we found that our p-value is basically 0, and our z-score is 10.18, so very high, very far away from what the middle would be, or what our 0.2 would be. So looking at that, it seems that we have strong evidence to suggest that that we're going to reject the null hypothesis. So now adding in our new thing, a confidence interval. So because our p-hat was 0.9091, and technically, since we really don't know what the actual long-run proportion from this is, I know that we make a hypothesis based on randomness, but we really don't know if that's truly the correct one. That's why we do the tests. So here, based on our confidence interval, we get to say that there is a 95% probability that our actual real-life parameter of long-run proportion falls in between 0.811 and 1.007. Now, to clarify, for our confidence intervals, they never take into account to obviously I can't have over 100%, that's what that 1.007 would mean, but sometimes they fall that way, and so don't read too much into that value being bigger or being smaller. That's just how it falls. So our real life long run proportion should fall in between that, and we're 95% confident, or the 95% probability of that happening. So here, for our conclusion, that we can make here is dogs can determine through their sense of smell whether or not someone has cancer if they're trained properly. Now looking back, maybe they want to try it with different dogs, or maybe they want to try it with different patients, or a different type of cancer. But that might be something to like solidify their evidence here. And so what I'd like you to do during class is to try example 2, doing the same thing, but adding in the confidence interval. The readout that I used was from the theory-based inference, but it'll work kind of the same way. Okay? Have fun.